So historically, we have understood that through experimentation, particularly by Galileo, we first found out with the Leaning Tower of Pisa experiment, which might or might not have happened, that objects with different masses, when dropped from the same height, hit the ground at the same time. Prior to that, our understanding was that larger objects or objects with greater mass would fall faster than objects with smaller mass. The same thing can also be proved by using inclined planes with equal angles. So if this is theta and this is also theta, then if you have a large object and a smaller object and you roll them down the inclined plane, within experimental error, it was found that both these objects gained the same amount of speed when they came to the bottom. So through verification by experimentation, not that we did the experiments ourselves, but by looking at historical accounts, we came to the conclusions that all objects fall at the same rate. But this conclusion is far from being clear to students of physics. If questions are straightforward, you might say, yeah, all objects that are falling fall at the same rate. But if the question were twisted a little bit, not very clear what was being said, I'm quite sure several of us will fall back to our Aristotelian self and say that it's not possible. Okay, so let us, now that we have learned second law, let us look at this particular situation of free fall from the second law's perspective. Okay, so what does second law say? The second law says that, and I'm using an example from the textbook. Let's say you have a brick, and I'm going to change the example a little bit, and you have a spring, a coiled spring, okay, against which the brick has been placed. Now if you release the brick, all right, the brick is going to accelerate and move forward. Okay, why does that happen? Because the spring exerts a certain amount of force on it. So there is a force that acts on this brick, the force applied by the spring, and because of that force there is an acceleration. All right, now if you did the same thing with two bricks, go back to the same color. If you did the same thing with two bricks instead of one brick, but use the same spring, okay, so the force that is being applied on the brick will be exactly the same, but the acceleration is a question mark. So what will happen to the acceleration?
It will half. It will decrease.
Yeah, so why do you say, somebody said it will half? I think it was, who was that?
Sir, it was me,
Pratham.
Pratham. So Pratham, you're saying acceleration will become half. Why?
Sir, because it's inversely proportional to the force. Sorry, mass.
Force is the same, mass. Okay, so you're saying, like, look at the equation again, right? To understand what is the acceleration that is going to happen here, we have to look at the equation. The force in both cases are exactly the same. Okay, it is the force applied by the spring, right? The mass, however, varies now. So in this case, we can write acceleration in the first case equals to force of the spring divided by the mass of the brick. So the brick's mass is mb, let's say. What is the case over here? Acceleration 2. The force on the spring is exactly the same as before, right? But what is the mass?
2 mb.
2 times mb. Oh, sorry. mb is a subscript. Okay, so now if you have to compare A1 and A2, so you can write greater than, lesser than, or equal to. What will you put in the box over here?
A1 is greater than
Greater
A2.
than A2, yep.
A1 is equal to 2A2.
Equal to? Somebody said equal to.
Yeah,
Somebody said,
A1 is equal to 2A2.
okay. So in other words, basically
Greater than.
A1 will
Greater than
be
A2.
greater than A2. Okay. So, oh, beg your pardon. So then, let us extend the situation even further and put 3 bricks now. Okay, same spring, same situation, 3 bricks. And let's say that they won't separate from each other. So now what is going to be the acceleration?
So,
Yeah,
1/3.
so this is A2 and this is A1. Okay, so you can see that in this case, the acceleration 3 will be the force divided by 3 times mb.
Yeah.
What I wrote dB,
MB.
mb. Okay, so therefore we can see now through the second law, why is it that when the mass increases, the acceleration keeps decreasing, provided you keep the force as the same. Okay, so how does this explain what happens in the case of an object falling freely, right? So let us look at that situation. Is this situation clear to everybody? Are you all able to understand?
Sir, I have two things to say.
Okay, so now just to put this in order, we'll say that A1 is greater than A2 and both of them are greater than A3,
A3.
right? So the
Yeah.
greatest amount of acceleration will be in this situation, least in this situation. Those of you who are able to see the mathematics, you will see that A1 is equal to 2 times A2 and A1 is equal to 3 times
3
A3.
times A3. Yep.
Okay, so that's another thing. That's just for those of you who are thinking along those lines. I'm just giving you a confirmation of that. But others don't bother with that. Yes, somebody had a couple of questions to ask.
Sir, it was me, and the first one is not a question, it's just a observation. Sir,
Yeah.
the acceleration vector should be, yeah, you made it shorter.
Okay, I was thinking of doing it. I just didn't get time to do that. Yeah, so the acceleration vector, I have to show it as smaller. So I'll just show that. This has to be half of A1, so I have to make it something like that. And this has to be 1/3 of A1, so I have to make it even smaller. So sort of like that, okay?
And
Can't do
sir,
it in scale, but yeah, that's the idea.
sir, in the third case, if we had three springs and they were all compressed at the same level, then
Yeah,
the acceleration would be equal to A1, right?
correct. You can look at it that way also.
Yeah.
Okay. So the thing is how to look at gravitational situation. Why is it that in gravity, acceleration always works out to be the same? Okay. So that's the part we have to understand now critically. So I'm going to erase this section. I hope nobody minds. This clear. That doesn't work. Okay, I just have to use the eraser mode. This is like being in school.
But sir, in school, erasing is harder.
I know. That's true. One moment, I just think Vashish is, he's here. Okay. All right. So let's look at the same situation for free fall. Now, what happens in free fall is, let's say you have a brick. Okay, and it's falling. Why is it falling?
The
Gravity.
gravity.
Because the acceleration is acting downwards.
Yeah, because gravity is acting downwards. So that is a force, and we know the value of that force. It is mg.
Yes.
Okay. Do we know what its acceleration is?
Yes.
Yeah.
What is it?
9.807 meters per second
Yeah,
square.
approximately equal to 10 meters per second square. Okay, so we know the acceleration and we know the force. So force is mg, acceleration is equal to 10 meters per second square. Do we know what is the mass? We
No.
can keep it. We can keep it
Not
simple.
yet.
Mass of brick.
Okay.
All right. Is this situation clear?
Yeah.
Yeah, sure.
Okay, so we can write acceleration is equal to F upon m, and we can write that as 10 equals the force, which is mb times g divided by mb. Do you get that?
So why is it MB times
MB
G?
times G, yeah.
Because
It's,
m is equal to m.
Because force is mg.
so I can write this as mb times g.
Yeah.
That is the
Okay,
force
now I
with
get
which it's being pulled down by gravity, right?
Yeah,
Yeah.
Fine?
Yep.
Yeah.
Okay. So now let's look at the same thing happening with two bricks.
Sir, I didn't get it. Why is it MB into G times G?
What is the force with which gravity is pulling that brick down?
G,
mg, not
MG.
g,
Yeah, MG.
mg.
So why are you doing? Okay.
Mass of the brick is mb, that's why.
Yeah.
You're just substituting.
Okay.
Yeah.
So now, same thing with two bricks. The force, if anything, is going to be greater, correct? Because it is 2 mb times g, correct?
Yes.
Yeah.
Yeah.
Yeah. So therefore, not therefore, but the acceleration is still going to be equal to approximately 10 meters per second square. That's what these experiments seem to be saying.
Yeah.
We are trying to verify it. Okay, so let us again apply the equation. Acceleration, oops, I want to do that in black. Acceleration is equal to F upon m. Okay, so the acceleration we are saying is still equal to 10. Why? Because the force we are saying is 2 times mb multiplied by g, but it's also divided by 2 mb.
2 MB.
Yeah. So 2 will cancel.
Exactly, they'll divide each other out.
So the same thing.
It's the same. Yeah.
It's exactly the same thing. Okay, and of course you can also then go ahead and do it with 3 bricks. I'll do it slightly lower than that, it doesn't matter, because the gravitational acceleration is always going to be the same.
There 3 will cancel out.
2 and 3 bricks falling under the influence of gravity. mg is going to be even bigger because it's 3 mb times g. But the acceleration is still going to be 10 meters per second square, right? Do the same process again.
Also, the mass increases, right? Yeah.
Exactly. It's the reason why the gravitational pull is always going to be the same is because the acceleration is also, sorry, the mass is also proportionately higher.
So
So
basically, everything cancels and we are left with G.
you are left with G, exactly. So acceleration is equal to F upon M. Again, I'm using second law. Acceleration is 10, supposedly 3 times mb times g divided by 3 mb. So now you see again, g is equal to 10 meters per second square, g is equal to 10 meters per second square, and g is equal to 10 meters per second square. So that's another way of looking at the fact that the acceleration due to gravity will always be approximately equal to, why do I keep going back to that? 10 meters per second square.
Second square.
Because although the force of gravity is increasing on each set of bricks, the mass is also increasing. So therefore, the acceleration proportionately reduces, because although it's directly proportional to force, it is also indirectly proportional to mass. So I hope this situation becomes clear. Any questions about this? Yes.
Sir, I
So
just want to say something.
Go ahead. Make a sequence and then speak.
Like, we can look at it like, if the acceleration is not, if the force is increasing 3 times,
Yeah.
the mass, the inertia is also increasing, right? If the mass is
Yes,
increasing by
it's
3
good to
times.
talk in terms of inertia. Yes, the inertia is also increasing. The resistance to the acceleration is also increasing proportionately. So
Yeah,
complete the
because the
statement.
mass is increasing.
Okay, next.
yeah, sir, I just wanted to clarify. So
Yeah.
even if there are two different objects, even if they'll fall, the mass will still be the same, and the and mg will increase. So then they will still cancel out, and everything will be the same, even if they're in
Yeah.
different objects.
Yeah, except that you said two objects of same mass. If there are two objects of same mass, then the forces acting on them are the same. That's not an issue.
Yeah, but if they're different, then it will be like this.
Exactly. So they don't need to be bricks with equal, but the reason why I used bricks was to sort of compare, to say that, you know, 2 bricks is twice as massive as 1 brick, 3 bricks is thrice as massive as 1 brick. So
They're
then you can
identical.
see the relationship.
Yeah,
But then
okay.
it doesn't matter if it's bricks or if it's cannonballs or whatever it is. Right? In all cases, it's going to work exactly the same, because the equation doesn't care what the material is made of, what shape it is in. It only says what is the mass, what is the force acting on it, and what is the acceleration that will occur as a result of that force. So I hope that point is clear. If there are any more questions. Okay.